Thank you. The title of my talk is A.I.M, Art, Intelligence, and Machine. I want to talk about these three topics and how they come together. I think of art as obviously an area that explores creativity for humans, but it's also an area of interest in terms of actions using the body. So I will talk about embodiment, skills and crafts, aesthetics, how we perceive, in particular the question of beauty, what is that? Representations, in art we think of how to represent the world, objects, scenes, context, in different ways, and it keeps evolving through our history. And art is about learning about the world. And if you think of it, every one of us, when we are a child, we explore the world and learn about it, in particular our relationship to objects through artistic activities in particular. I will talk a little bit about intelligence and try to give you some basis to understand what we mean by intelligence, but I will emphasize those aspects of intelligence that makes us different as a species, as Homo sapiens sapiens. We'll talk about machines and how they have co-evolved with art, and how is this all related to AI. I think of AI mainly as a field where we study human intelligence, where we test ideas about human intelligence. And this goes back to the origin of AI. So if you look at the history, the agenda was initially set in that context. But of course, as AI becomes more and more effective, it also becomes a way to extend our own intelligence. As an example of how these topics come together, I will talk about two different projects. The first one took place about 10 years ago, and it was a collaboration with Patrick Tercet, a French artist, and we produced a system that you see here an example of called Paul the Robot, a system that's able to do portraiture in the style of the artist, Patrick Tercet. The agenda is to really try to understand how humans perceive faces and conceive of a set of actions to re-render this, re-represent, if you want, the face here in the context of a sketch or a drawing. Of all the little parts that you see in this high-level diagram, initially we could only focus on a few of them. We've mentioned computer vision in the previous talk, and this is sort of the approach we took back then. We did explore a little bit of feedback, so the computer vision via camera could be used to measure what was done on the paper, and there could be some feedback loop. At the time, we had no technology to address some of the eye-level features such as experience or the past, the memory, a feature that nowadays can be captured through machine learning techniques. Initially, we built a purely computational model, and these are examples of portraiture done in the style of Patrick using a simple computer vision approach, no robotics involved. And you'll notice the quality of the traces are sort of systematic, so they are machine-like. To go beyond that, we decided to embody our system and build our own robotic arm and camera system, a robot called Paul, which has uncertainties linked to the design of the arm. So the arm here, the robot, is not meant to be very accurate in a similar way of how we use our own body. So here a short video that will illustrate that system, which has been presented to many audiences around the world since those days. So the camera system looks around in the scene, finds a face, and then goes at its work. And in later versions of the system, the camera is actually used to look at the drawing as an artist would do in general. You usually don't work only from memory. until you reach a final portraiture, and you have notion of here, when do you stop? It becomes an issue. Finding a signature. More recently, work which evokes some of the work of Sugwen in maybe a simpler way. So here you have a collaborative mode where, in this case, the artist provided an initial input to the system, to the machine. The machine observes the result and then starts adding their own stylistic signature to the portrait. So this is work by Patrick Tresset from a few years ago. Patrick himself now has left Goldsmith and runs his own studio. So I've given you an example of how these systems or these topics come together, but I want to say a little more about intelligence. So here I want to give you at least some background. I take the view of so-called cognitive horizon, and this is a definition given by people from different fields. Here in particular, I'm taking the definition from Michael Levin and Daniel Dennett. Michael Levin is a biologist. Daniel Dennett is a philosopher. And essentially, we have a definition that allows us to build notions of intelligence that apply to all species, including potentially synthetic life forms and AI. Mainly, the two main aspects of this definition are that there are spatial extent to cognitive horizons, in particular how far away the agent can sense and exert actions, and actions here is key in the definition, and there's also the time dimension, notions of memory, again, that we mentioned before, and also anticipation, predictions. So different species will have different spatial extent, different time extent, and achieve different levels of cognitive horizons. What's interesting here in this kind of definition as a basis for intelligence is that it implies the need of a body. Why? Because this notion of intelligence access directly acting in the environment. Now, as I mentioned before, I want to focus on what makes us different as a species. So I've come up, or I tend to say that there are three main areas that distinguishes us from all other species. They are the first three here. Art, very generally, by art I mean any creativity involved activity, so covers music, for example, dance, etc., as well as writing. And we could look at the history of art all the way from cave art, for example, or rock art, which eventually evolves and gives rise to writing, symbols, and eventually mathematics itself. Machines are there from the beginning as well. We needed tools to be creative, and the evolution of machines can be tied up with the evolution of our creativity potential. Language is, I think, the third major topic that distinguishes us from other species. We could go into all the details of that and see how all this is connected. And as an outcome of these three distinguishing features, we have also this specificity that we can continuously increase our cognitive horizons, which is very different from any other species we know of. And this is applied not only to humanity over history, but actually to our own self during our lifetime. So you got the main message, I hope, from how I see intelligence and how I work with art, machines, tools of all kinds. Just to conclude my talk, I want to give you a little bit about what we do these days. So after the work with Patrick Tresset in particular, I started to work with another artist, Daniel Berriot from Italy, who's an expert in graffiti art. And we decided to go a bit beyond and focus on the importance of movements, and especially gestures that are used when you create an artistic piece. It turns out that there's a lot of work being done in different scientific fields, and in particular in psychology, and also to some extent in neuroscience. It's been observed that The individual who observes the results of traces on a canvas can actually guess what type of movements very likely were used to create the traces. And this informs our aesthetics, or how much we judge the quality of the traces that have been laid on a canvas. And here's a simple example in calligraphy, where if we ask different people from a psychology point of view, they will be overall coming up with similar answers. How was this calligraphy done? Not only where the traces were put, but also at what speed, what acceleration was used as well. The work since about 2015 has involved different teams. Here you see a sort of list of some of the major players. You have people in graphics, in robotics, in Switzerland, for example. People also in psychology at Leuven. So graffiti itself is a modern form of calligraphy, and it's performed by experts, artists, with very rapid movements. Here's Daniel and some example of the art he can produce. By the way, if you're interested in the work, he has published his thesis recently, and I can give you pointers. There are different types of scientific results on how human experts move. And this comes from a field in particular called graphonomy, a field that emerged in the late 70s, early 80s. The goal at the time was to understand how we write, and in particular, how we sign, banknotes in particular, to try to uncover falsification. Over the years, a few models have emerged that characterize well how a human, when they have developed an expertise at a trace, you can think of your signature, how they move. And the particular model we focused on is called the sigma log normal model. And it takes the form of these bell shapes that you see here. So essentially these point to how fast you start moving to a maximum speed and then come down to a lower speed. And you can use this model to create from different targets. You have here on the left-hand side 3 targets, a starting point, a middle point to try to reach, and an end point. And with the same model of your kinematics, your speed and acceleration, by acting in that space, the space of movement, you can derive different versions of trying to reach similar targets. And this turns out to be a very good model to address how we get good at doing things like calligraphy. You have a tag on the right-hand side as an example, and the underlying understanding of it is this bell-shaped model. So just to give you an idea of how this works, once you have this model, you can create all kinds of interfaces. Here's an example that links to traditional computer graphics. And one of the interesting differences with traditional models like so-called splines or Bezier curves is that you can act in the world of kinematics rather than in the actual world of traces to create variations on your outcome. And this is, so this is illustrated here. You have a Bezier variation on the bottom where you try to increase different examples by varying the positions of the so-called knot points, and then you have access to our model, which is based on movement, which leads to more agreeable results and is easier to easier to control. So once we have a good computational model, like the model we just illustrated briefly, we can think of making it embodied in a robotic system. So this is very similar to what we did with Paul the robot more than a decade ago. We started to try to understand computationally how the artist was producing a portrait of a certain style. Once we were satisfied, we moved to a robotic system. So we are doing the same thing in more recent years in the space of characterizing movement in calligraphy. And this is an example. So first you run simulation, which is traditional to do in robotics before you move to actual robots. And again, what's interesting here is the quality of the trace that you can achieve. So these are the kinds of robots we work with, so-called humanoid robots, which are safe to work with, where you can, they're called compliant, so they will actually stop if they encounter you on the way. They're safe, again. Here the robot is learning from errors with respect to these targets and eventually achieving a better quality of traces. And then the system can start doing traces in a particular style, here a particular type of graffiti style. And for us, this is a sort of a demonstration that the understanding we have of movement can actually be embodied and being shown to be close to what the human expert might do. These are early work in that type of application. So getting near the end of my talk, I just want to reemphasize some of the main messages here I wanted to give you. In particular, we should think of intelligence in relation to our body capacities. And in a large way, what we observe in AI and robotics these days can make us think how to go beyond the body capacities we had in the past. Where do we go next in our case in terms of our research agenda? So we're looking at working more in the domain of painting these days and collaborating with people in many different fields. And here you have a few listed, including cognitive scientists. There's an ongoing collaboration, so here I'm just doing a little pitch for our work, with a very strong team in Constance University, led by Professor Deussen, who established a robot painter system more than a decade ago now, and this is progressing, called eDavid, if you're interested. And together we are leading a new project called Embodied Agents in Contemporary Visual Art, which is funded by the UK and by Germany. This is a team, and I think what's interesting there is the different collaborators across different nations, across different disciplines, including areas like philosophy. So, my last slide. I've pitched an idea of how to think about art, intelligence, and machines coming together. And I'd like to re-emphasize the importance of art, and here I mean really all domains linked to creativity, in progressing our understanding of intelligence in humans, but as well, I think it should play an important role in the near future of AI and robotics. Thank you.